So one of the surprises, one of the biggest surprises that the New Horizons spacecraft gave us, from its flyby in 2015, was that Pluto actually has a really uh, kind of a well, it has an atmosphere. It's an atmosphere that has nitrogen and carbon dioxide, or sorry, carbon monoxide. There's a little methane in there as well. But it's not much of an atmosphere, but it was still a surprise. The other thing is, if you see this heart-shaped feature on one side of Jupiter. I'm sorry, one side of Pluto. Um, this Notice how flat it is. Remember, the basic idea here is that when an object is uh, not very cratered, that means it's a relatively young surface, and that's a little bit surprising as well, because look, the temperature of Pluto is around 40 Kelvin, right? So, or minus 387 Fahrenheit, right? That is extremely cold. And so how is it that the surface feature could be so young, right? That implies that there's something going on that's causing the surface features to change um, in relatively recent geological history of Pluto. So that was a big question mark. Um, we think it actually has to do with the nitrogen ice melting, or actually sublimating, undergoing sublimation, turning directly from ice into a gas. In fact, we think that's where the atmosphere comes from, um, and it really has to do with the extreme eccentricity of Pluto's orbit. Even, I mean, it doesn't get that close to the sun, but it does get a little closer to the sun. And when that portion of its orbit here, let's go back a little bit, right here. So when it's getting a little closer to the sun, this period right here, um, then it warms up, and you're going to have some of the solid nitrogen turning into a gas. And what we think is that's affecting the surface as well. All right, so that's another thing that we noticed here. Let's get along. Is to see this brownish area in on Pluto, and actually on Charon as well. There seems to be organic compounds, like, in other words, carbon-based compounds, not certainly not living things, but stuff that is the basis of life, right? The molecules that form the basis of life. This stuff these are called tholins. That's just a generic term for these carbon molecules, carbon rich molecules. All right, so out beyond the orbit of well, for the most part, beyond the orbit of Neptune, um, with the exception of Triton, which of course orbits Neptune. Now, you see, it turns out that Triton and Pluto are very similar in composition. Of course, Triton is much bigger, but their composition turns out to be very, very similar. And remember, Triton, if you go back to when we're talking about Neptune, Triton goes backwards in its orbit around Neptune. In other words, it's rotating around Neptune clockwise, whereas Neptune and the other planets, for the most part, are spinning around their axis in a counterclockwise way, and that's the same way in which they go around the sun. All right. So, as I said, Eris, as I mentioned before, Eris, where is Eris? Oh, there it is, right there. When Eris was first detected, I think the year was around 2003. Um, it was believed to be slightly bigger than Pluto. Nowadays, we've revised our measurements, and it's actually a little bit smaller than Pluto. So actually, Pluto is now the largest member of, at least the largest one that we know of the Kuiper Belt. And remember, we also think that because of this bizarre orbit of Triton, we think that Triton is a captured Kuiper Belt object that somehow got too close to Neptune and ended up in orbit around Neptune. And so this would have been the largest Kuiper Belt object. Here are some other Kuiper Belt objects. Sedna, which is a really distant object. I mean, we're not exactly sure how far out the Kuiper Belt goes, but we estimate that it extends out at least at least 50 astronomical units, perhaps more. I mean, I wouldn't be surprised if someday in the future we find something out 100 astronomical units away from the sun. But right now, the stuff that we have found has all been within about 50 astronomical units of the sun. Remember, Pluto is at 40 astronomical units from the sun. All right. So there is some argument about a possible ninth planet out there beyond the orbit of Neptune. Not Pluto, of course. And the reason for that is there's something that seems to affect the orbits of the Kuiper Belt objects, and whatever is doing this, right? Whatever is causing this, it must be some massive object. Some people have calculated the mass of this object is more than 10 times the mass of Earth, which would, in other words, it would be like another Neptune or another Uranus, but it would be much further out, way out in the Kuiper Belt. Again, no one's ever seen this, but there seems to be hints of it, at least when we look at the mechanics of the orbits of the Kuiper Belt objects. There seems to be something that is causing these things to orbit the way that they do. But again, you still have to actually go and find this object if there is indeed a ninth planet out there. You have to actually go and detect it, and up to this point, no one has. All right. Now we turn to comets. So comets are depending, the different comets are different in the sense that some of them are very, very bright in the night sky. Some of them are extremely dim, and you need a telescope or binoculars to see them. Some of them are so dim that you would need like a really powerful telescope, like the professional telescope, the kind they only put on mountains to actually see them. And comets don't always keep orbiting the sun. There are situations where comets will come into the inner part of the solar system and just crash into the sun, and that's it. It's kind of a one and done situation. All right, so there's three main parts of the comet. Let's start with the nucleus. The nucleus is the part that it's sometimes called the dirty snowball, and on average they're about 10 kilometers in diameter. So that's about 6 miles across. So these are relatively small objects. There are asteroids that are smaller than this, but there's a lot of asteroids that are larger. Then there is a region right outside the nucleus called the coma, and that is where you have gaseous material that is actually coming from the comet, coming from the nucleus, this dirty snowball, that is escaping out into space. When the comet gets closer and closer to the sun, then it develops a tail, and the tail can be huge, right? So some of them are as long as 100 million kilometers. Now think about that. That is 2/3 the distance from the Earth to the sun, right? That's a huge portion of space. sorry about that. This is a huge portion of space, and so that's generally what you see if you actually end up seeing a comet, is this incredible tail across the sky. Now we've sent spacecraft. The Giotto spacecraft was the first one when Halley's comet came close to the Earth, close to the Earth and the Sun the last time, which was in 1986. Then we actually sent a spacecraft to take a look at it. It measured the density of it, and of course, it confirmed the fact that comets are basically dirty snowballs. They're made of icy material, and the icy material is it sublimates, so it doesn't go. It doesn't melt when it gets closer to the sun. What's happening is the ice turns directly into a gas, and that's what you see. You see this long, long tail, sometimes 100 million kilometers in size. This is kind of a close up of Comet Halley. Comet Halley is probably the most famous one. One of the reasons, of course, Halley was a guy that lived during the time of Isaac Newton, and he actually discovered historical evidence that there was this comet that appeared every 76 years, or 75 to 76 years. And so he said, hey, well, wait a second, why does this seems to be an object that's orbiting the sun? And so he went to the smartest guy he knew during his time, and that smartest guy was Isaac Newton. And so Halley went to Newton and he said, hey, is there any mathematics that describes the orbit of an object that would be going around the sun? And of course, Newton, being a very brilliant mathematician, as well as a brilliant physicist, said, yeah, I have some equations that describe that. And of course, Newton had invented calculus and had kept it quiet for a long, long time. It was actually Halley who encouraged Newton to publish this great discovery. I mean, and it really was a great discovery, the likes of which it's hard to describe what the world would be like without calculus. It's an incredible mathematical tool, especially in engineering. I'll just leave it there. All right. So the thing about the comets is the radiation from the sun. The sunlight always offers pressure, and so the tail, what's called the dust tail, always points away from the sun. All right. So here, this is an example. There's the dust tail. There's also this ion tail, which is just charged particles coming off of the comet, and the ion tail always points along the sun's magnetic field. The sun has the strongest magnetic field in the entire solar system. So as a comet comes in towards the sun, it begins to sublimate and it develops a tail. The tail gets longer and longer, but notice it always points away from the sun. All right, so that, and you may or may not see the ion tail. It's really the dust tail that we generally can see from the Earth, from the Earth. So comets they keep losing their material every time they orbit, right? And now Halley's comet has been doing this for centuries and centuries, but eventually over we think probably, a million years from now, or even less than that,